Good evening, everybody. A warm welcome from ICI Kochi and QCrete to this webinar. As you all know, most of you might have attended other webinars also. So this is a series of webinars that we are conducting in association with QCrete, and we have been striving to bring to you the most contemporary topics in civil engineering. And there is none other than Professor KVL Subramaniam, who can talk about this very important topic, which is a hot subject of research and industry concern, which is sustainability. So today we have a talk on making concrete sustainable and moving towards a net zero. So now I would request Kaushik ji to take over and introduce the guest.
Thank you, madam. On behalf of QCrete Readymix India Private Limited, who is conducting this webinar in association with Kochi ICA chapter, we are honored to have Dr. Subramaniam today here. It is remarkable that such a giant in the civil field accepted our invitation, and we thank you, sir, for this gesture. I'll just introduce Dr. Kolluru V.L. Subramaniam. Professor KVL Subramaniam is currently a professor in Department of Civil Engineering at Indian Institute of Technology, Hyderabad. He is the Dean, Planning and Development at IIT Hyderabad and is overseeing planning, design, construction of the campus from 2011 to 2017, 2020 to present. The construction cost of the campus and its facilities is around 2,500 crores. Dr. Subramaniam sir is completely in charge of this project, guiding them. He was the founder, head of civil engineering department at IIT Hyderabad 2010 to 2015. Prior to joining IITH, he was professor of Capital Research Fellow in Department of Civil Engineering at Grove School of Engineering, the City College of Newark. Dr. Subramaniam obtained BTech in Civil Engineering from IIT Delhi and PhD in Structural Engineering and Materials from Northwestern University, Evanston. Dr. Subramaniam was awarded the Early Career Award from the National Science Foundation, NSF of USA. He received the James Instrument Award from the American Concrete Institute in 1999 for his research on non-destructive evaluation of concrete. He was the chairman, Committee 215 on Fatigue of Concrete of the ACA in 2009. He was elected a fellow of the American Concrete Institute ACA for notable contributions to concrete materials. He is an associate editor of Journal of Materials and Civil Engineering of the American Society of Civil Engineers. He is on editorial board of Journal of Cement and Concrete Composites, Elsevier. He was elected a fellow of Indian National Academy of Engineering in 2021 for notable contributions to concrete materials and structures. He is an active member of CED2 of Bureau of Indian Standards and committees of FIB. And his areas of interest are structural engineering and mechanics, rheology, 3D concrete printing, alkali activated binders, strengthening of concrete structures, fiber reinforced concrete, fracture of concrete, embedded sensors for concrete structures. The list is very big and it is very difficult to captivate or capture in this short introduction. Once again, we are thankful to you, sir. And now the floor is yours. Thanks a lot.
Thank you, Kaushik Garu, and thank you, ICI Kochi Center, for giving me this opportunity. I selected a topic that is relevant today, and it's a very vast topic. So the topic actually is of immense relevance today. So let me actually start my presentation. Let me just make this full screen, then we can get started. I want my mouse, but Just one moment. I'm just trying to make it full screen. Sorry. Okay, so now it's full screen. I hope my audio is clear.
Yes, sir.
Yeah, okay. So I'll get started with the presentation. So the topic that I'm going to talk about is making concrete sustainable and moving towards net zero. And this is covers a lot of things, and this basically presents on things that are going to come as they develop. And this is something we need to prepare ourselves, particularly with the use of concrete in construction. And the issue is that concrete, of course, I'll be preaching to the choir here, is it's one of the most widely used materials in the world. On an average, more than 2 tons, of course, of this material are used for every human being on this planet. And it is the second most used material on this planet, of course, the largest manufactured material that's used. So there is no wishing away concrete. Now, the problem becomes even more acute in the Indian context, because we are a growing economy, we are an emerging economy, and the bar graph that you see there is what has been the growth or the percentage growth of our GDP every year. But for the 1 year where because of COVID there was a negative spike, you see that we are actually increasing, and on an average we are hoping to hit about 6 to 7% growth, and a good year probably 8 to 9% growth. Now that is not going to happen unless we modernize and expand our infrastructure. Infrastructure in the form of roads, infrastructure in the form of bridges and transportation, housing needs have increased. And the estimate that we have in India is that we need to be spending about $1.2 trillion by 2030 to meet the projected demands in the cities, projected demand of infrastructure. This is required for us to sustain our growth. Now, the growth contribution from productivity will be higher than in previous periods, and that is the other thing. That is, if we are going to, if India seriously wants to be a $5 trillion economy, we have to start creating physical infrastructure, and we have already started that. There's significant investments being made in our transportation infrastructure, housing, because as we urbanize, there's a heavy demand for housing. And so there is, all of this requires a lot of concrete. And the problem is with concrete is this cement. So if you look at it, cement, a clinker, makes up about 10% by mass of concrete. So if you look at this here, basically you start off with clinker. That is a basic material that we use for making cement. And by the time you come to concrete, its percentage is diluted to about 10%. So that is how much clinker goes into concrete. But if you look at the carbon footprint of this concrete, the clinker makes it about 90% of the carbon footprint of concrete. And carbon is the one word, it has become a dirty word. Now we need to handle this. And the main topic of my talk has been going towards net zero. And what we imply by that is we want to become carbon neutral by 2050. It's a target that's been set for us, and we have to start moving in that direction. And the problem here is with this clinker here. So that is one of the major contributors for carbon in concrete construction. Now here, of course, there are two players in this particular market. You have the cement producers who are looking at it primarily from the cement perspective, but then ultimately it ends up being used in concrete. So I think we really need to look at net zero from a concrete perspective, a material perspective of concrete, where clinker is the major contributing factor. So that is what we have to look at. And what is the cement scenario? What is it that we are currently looking at? So if you look at the cement production in the world today, China, of course, leads by far everybody else. It produces more cement than everybody else put together. But India is the second largest producer of cement, and all of our cement production is captive. Whatever we produce, we consume. There's nothing left for any export. And the demand for cement, if you look at it past, present, and future, this is where we stand. Now, China's demand is peaking, and we expect that the demand in China is going to go down, but India's demand is only going to increase. The projected demand of cement in India is estimated to be around 750 million tons per annum by the time we hit around 2030 and a little beyond that. So there is a humongous requirement of cement, a very large requirement of cement, projected requirement of cement, and this is required primarily for concrete that we need for putting all the planned infrastructure that we have in mind. Now, if you look at cement itself has a low embodied energy. It is amongst the lowest of all materials. If you compare it with steel, glass, aluminum, the embodied energy is very low. But the issue is carbon, where cement per ton or per gram of cement has a very large carbon footprint. And combine this with the very large volume requirement, then we are looking at a very large carbon footprint associated with cement. And this is the worrisome aspect which we are dealing with. And this is where we have to work on in trying to chip away at the problem, trying to solve it. So now, where are the challenges in cement production? So it's not like we can continue to make cements. And if, like I said, our projected demand, if it is going to be 750 million tons, for producing cement, we need limestone. And the current reserves of limestone, the good grade limestone that we need to make cement is estimated to be around 35 to 40 years. Of course, this is to this day, we don't have an accurate fix on this, but we estimate it's going to be 35 to 40 years. Cement companies will tell you otherwise, but this is one of the major limitations. So there is a resource limitation also that is looming. So if we want to make the cement that goes into making the infrastructure, we have to look at this resource limitation as well. There's an energy requirement for producing cement. Cement is an energy intensive material. Compared to other materials, the energy footprint of cement is much smaller, but still it requires a lot of energy. And this is the major worrisome factor, the carbon footprint that associated with cement production. And this is what we are trying currently to tackle and trying to bring down the carbon footprint of cement. So if you look at the production of clinker, because if you look at concrete, the primary carbon tag associated with concrete, 90% of the carbon tag comes from clinker or cement. So if you look at cement production itself, most of the cement, the carbon comes from two sources. One is the process itself. I have to decompose limestone. My basic chemistry is limestone chemistry. We basically take limestone, we heat it, and it gives off carbon dioxide. So this is inherent in the process of making cement. Carbon dioxide is going to come out no matter what, because I heat limestone and that gives off carbon dioxide. There's also another part of the carbon tag associated with cement production that has to do with thermal, which is basically the heat that is required to break this limestone, and heat that's required for clinkering process. So that also has some carbon tag. Now, I can tackle this part of it, the thermal emissions, because now when we're looking at net zero, we've learned to dissociate the carbon produced during the manufacturing process with the carbon associated with energy, because I can produce or I can meet my energy demands coming from renewable sources. So basically, I can make this entire half green, but I still get stuck with this because of this process here. So one of the fundamental issues with cement production is this. It starts off with limestone and I have to decompose it, and there in the process itself there's a carbon tag associated with it. So basically, this is just a slide that shows you the different processes that are involved in the production of cement. And if you look at the energy consumed and the carbon dioxide that's produced, most of it goes into the calcination and the clinkering part of it. And these are the steps that now currently we are focusing on, trying to see what can be done in order to reduce the carbon footprint associated with cement. Now, if you look at the cement scenario and why is this worrisome, is that currently, of course, this is the chart that you see here is a breakdown of the carbon greenhouse gas emissions from the different sectors. And what currently the estimate that we have is that cement production accounts for 8% of the anthropogenic carbon dioxide. And it is the second or the third largest, depending on which source you're looking at, second largest or third largest source of anthropogenic carbon dioxide in the atmosphere. So that is the worrisome aspect. And the reason why it's 8% is because of the sheer volume that of this material that is consumed. And the concern comes from the fact that sooner or later, this is going to come into play. A polluter has to pay. And so it's a matter of time before carbon taxes or some kind of punitive measures are introduced for large carbon emitters. At that point of time, that then is directly going to impact concrete production, because the cost of producing cement is going to increase, either directly because of taxation or some kind of punitive measures, or indirectly where we'll have to offset the carbon with some other greener sources, and that essentially costs money. So this is going to net impact the cost of our infrastructure production. And this becomes even more pertinent for India because we are sitting on the cusp of our development, where we have to produce infrastructure. We have to continue producing infrastructure. Most other countries have already produced the infrastructure. Now they can, they do not have a demand for infrastructure. Our demand for infrastructure is only starting, and it's only going to grow, which means that for us, it becomes an impending problem. We have to look for this and seriously start looking at how to make our cement more carbon friendly. So people have already started working on this. There's also a roadmap that has been developed in terms of going towards net zero, and there are different measures that have already been thought of. So this is like a roadmap over the years, assuming that we become carbon neutral by 2050. Starting from 2020, this is the line that would tell you, going towards the net zero, the projected net zero pathway, as we call it. And there are different measures that already are being thought of, and the percentage contribution of these different measures are also kind of listed here. So the different measures could basically vary from as simple as efficiency in design and construction. I'll talk about this a little bit. So we really have to get more efficient in our design and construction. Efficiency in concrete production, and savings in cement and the binder. So in terms of how much clinker we can save, savings in clinker production, and then finally carbon capture, utilization, and storage. So this is something that is also has to be done, because I'll show you later that with all these other measures we can only achieve so much. And at the end of the day, if I'm going to use clinker based cement in producing concrete, I cannot completely eliminate the carbon dioxide that's coming from limestone decomposition. I can reduce my clinker factors in my cement. I can make my concrete construction very efficient, so I use very little concrete, but still I have to use some clinker, and the clinker will have some carbon. And therefore, this carbon capture, utilization, and storage is seriously being thought of as a major contributor in the future, to the extent of 36% of the total the contribution towards net zero will likely come from this. So this is a technology where a lot of people are currently focused on, is on the carbon capture and utilization, with varied levels of success. So, and of course, then there are other things which will have smaller contributions, like decarbonization of electricity. So basically, the energy can be made green with renewables, renewable sources, and carbon dioxide sink through decarbonization. This can be done within cement during hydration, or in aggregate, like recycled concrete aggregate. So this is like, these are the different measures, and by doing all these measures, chipping away a little here, a little there, we hope to achieve this net zero in concrete. And this is anyway a target that has been set to for us by our honorable Prime Minister of achieving net zero. So basically, if we are to be serious about it, we have to start thinking about all of these steps. Yeah. So what are the solutions for reducing carbon at the concrete scale? So if you look at this, then of course, there's a whole list of these things here. We're already looking at alternate cements. So we're looking at low clinker factor cements. So produce cements with low clinker factor. So since clinker is the one that is associated with a large carbon tag, then reduce the clinker factor. Alternate clinker-free cement binders. So alternate binders which don't depend on clinker. So those are also being developed, and or with cements with very low clinker factors are also being developed. Then the other thing that we are looking at is producing long-lasting structures. So if I have structures that last a long time, there's a lesser need for replacement of these structures, and therefore, in association, then I have a more sustainable process, which basically allows me to use the structures over long term without the chance of or without the requirement of replacement. But then, of course, I have to pay particular attention to durability, and also talk about performance-based design. So our current design procedures really have to be revamped. I'll present about this a little bit next few slides. Efficient construction is a must, because we have to reduce labor-intensive processes, make the whole process efficient, and we are looking at perhaps from pre-construction, very efficient structures with minimal use of material. And energy recycle and reuse is going to become pretty standard. So we are looking at low energy in the production of cement, concrete, and of course, bringing in recycled materials, and recycled aggregate concrete is already finding its way into making of concrete. So now, where do we stand with cement and making reductions in cement production? Of course, I'm talking about carbon. The Indian cement industry, I think, has already come a long way. So today, cement plants in India are run at a very high level of efficiency. We are, in fact, probably have some of the most efficiently run cement plants. And today, the cement industry has reduced the CO2 emission levels by about 36%. There's a significant reduction that's been achieved, to the point that today we're talking about 665 kilograms of carbon per ton of cement. So this previous number used to be much higher. We were at 950 kilograms of carbon dioxide per ton of cement. That has been decreased to 665 kilograms per ton of cement. So this is through process efficiency in the production of cement, bringing in renewable sources of energy for cement productions, and a slew of other measures. We are able to bring that number down significantly. The other thing we are doing is we are starting to produce a lot of cements with reduced clinker content. We are the only country in the world that is currently marketing and using cements like PPC and PSC. I'll talk about these in significantly higher detail in the next few slides. But now today in India, we're consuming more blended cements than anywhere else in the world, to the point that 73% of our cement consumed is primarily a blended cement. In terms of energy, we're talking about use capacity of waste heat recovery systems in the cement production. These have contributed to significant energy savings compared to previous baselines. We're talking about use of alternate fuels, where even things like municipal solid waste is being used for generation of the energy that is needed in clinkerization. And the target of the cement industry is to basically go to about 30% replacement of regular fuel with the alternate fuels, which then kills two birds in one stone, where I'm able to discard a waste and also use the energy that comes from burning the waste in a clinkerization process. Right. So now just briefly about this carbon capture technology and intervention that people are talking about. This is a schematic that shows typically what happens is, after production of cement, we have this flue gas that is emitted from the stack. And the flue gas contains about 14%, roughly 14% of the flue gas is carbon dioxide. And that carbon that is being emitted in the flue gas, now we're talking about capturing that carbon. And the way it has to be captured is that we need to bring up the concentration of carbon dioxide gas from 14% to 100%, make it a saturated or 100% carbon dioxide gas. Then you put it to use in either sequestering it, binding it somewhere, or storing it somewhere. So this is where I think a lot of technology is being developed, and where we are looking at extracting this carbon dioxide from the flue gas and essentially concentrating, providing like a solid concentrated carbon dioxide, solid or in a gaseous form. And there are different currently technologies that are at play here. We have the chemical absorption method, the direct separation, oxy-fuel, calcium looping. These are all at different TRL levels or technology readiness levels. Some of these are probably going to come to fruition soon, where we'll have this technology available for us to capture carbon, basically increase the concentration of carbon from the flue gas. And then the sequestration. What do you do with the carbon that has been captured, that is in the concentrate form? One of the solutions that is being thought about is sequestration, and one place to sequester it is in old discarded wells, oil wells, for instance, is to simply pipe it down the oil wells. Now the oil wells themselves have porous rock, which used to contain oil. Now they're depleted because oil has been extracted. So we take this concentrated carbon dioxide, which could be in a gaseous or a liquid form, pump it down the well, and essentially when that well gets saturated, just plug the well. So this is what is being thought of in terms of sequestration. So this is as we go to net zero, I think the projections show that if we are going to use limestone based cements, this becomes essential. We have to in some form capture and sequester carbon dioxide. Now, what are the different actions, like I mentioned about, in going towards net zero? So if you look at it, these are the different actions that are thought of. Now, first thing, like I mentioned, is efficiency in concrete production. Now, here we're talking about optimization of mixed design, quality control, going towards high performance and durable concrete structures. So this is one part of going towards net zero. And the whole point is this also brings in sustainability, because then I have a structure that is more sustainable. It's durable, it's going to last over a longer time. So it basically makes for sustainable production of concrete structures. So if we look at this now, I'll briefly talk about this. With this now, we cannot go with our conventional method of design. And this is, we're talking about concrete mixed design and even concrete structural design. The conventional method of design are prescriptive, and most of these are strength-based. And basically, we look at concrete material strength or structural member capacities. Now, if I really want to implement something that ensures durability of structures, it ensures long-term performance, then I have to bring in a performance objective. And here I have to talk in terms of performance-based design. Performance during formation and placement, this is also becoming very important, and performance during service life. These have to become essential criteria in determining concrete that goes into a structure. I'll just give you an example of high performance concrete specification. So if you look at the concrete that was placed in One World Trade Center, specifications are put in place. So you have specifications of this form where the cement usage in concrete was specified to be less than 236 kilograms per cubic meter of concrete. And this was for concrete that was expected to achieve compressive strengths of about 90 megapascal in the first 40 floors, and a compressive strength in the range of 65 megapascal for the higher floors. So expectation was that these high strengths could be delivered using a very small amount of cement. Of course, this would then only be possible if you look at mixed design very carefully, optimize the use of cement, and if we start looking at other materials, other cementitious materials, which have a lower carbon footprint. Now, there are also performance requirements that were put in place. That is, there was the concrete mixture that is produced had to have the ability to be pumped for at least 15 floors if it's a 95 megapascal mix. And if it's a 80 megapascal mix, it should be pumpable for 40 floors. This is a performance requirement that is specified. The maximum heat of hydration was specified at 70 degrees Celsius. Now, these are, and of course, there are other performance requirements in terms of measured performance in a specific test like the RCPT, rapid chloride penetration test. So these are all specified. Now, where is this different from a prescriptive measure? Well, strength in this case is something that is anyway expected, but there are other performance requirements that are now stipulated. What the material supplier does is not of consequence, but he or she has to meet the desired performance in the finished product. So this, I think, is the direction that we'll all be moving. A lot of codes are already moving, and I think our IS 456 is also headed in the same direction, where we will have performance-based requirements, where we will expect concrete to perform in a given environment. And that then would automatically ensure durability and an assured long-term performance. Now, coming to the other small chip in the whole game is to save on the cement clinker. And we can look at clinker substitution, and we can look at alternate binders. And to look at this now, we need to understand cement a little bit. And we know that cement is a manufactured material, and it's primarily, the primary ingredients that we have in cement are calcium silicate. So it's a calcium silicate chemistry that we are looking at when it comes to cement. Now, the way we typically look at cement is, if I look at the primary ingredients of cement, the tri and the dicalcium silicates, they react with water through it's a hydration reaction, and what I get is calcium silicate hydrate, and a lot of lime is produced. And initially, it's now probably 5 or 6 decades old, we've discovered that if I add a source of silica in the form of fly ash and slag, then I can produce additional CSH. So the initial attempts were to add them as additives, and we found that we were getting enhanced strength because there was the silica that was consuming lime and giving us additional CSH. Soon we discovered that I could use these as cement replacement instead of addition. And of course, then one has to get the math correct so that I can balance out the additional CSH against whatever it is that I'm losing with the reduction in C3S. And that has given rise to the production of these blended cements. So if you look at OPC, this is typically clinker 95% and gypsum is about 5%. Today, we are producing blended cements in the form of PPC, where I have clinker and fly ash to the tune of 30% and gypsum 5%. So basically, my clinker factor is already decreased. Now, I can decrease my clinker factor even more if I go to this should be PSC, to the slag cements. Here, the story completely reverses, where I can go up to 70% of slag and only 30% of clinker. So now the story is completely reversed. So here I'm talking about a very low clinker factor cement. So it'll definitely have a net positive impact on my total carbon contribution coming from the cement. Now, if you look at the blended cements, this is the story as it has evolved over the years. And today you see that 70% of the cement that you have, more than 70% of the cement that we're making is in the blended form, whether it is PPC or PSC. The problem is that with slag, we don't have adequate slag. We don't have enough slag that we can start making more of PSC. Otherwise, we could really bring down the clinker factor in cements and start looking at a reduction in, if you look at the greenhouse gas emission, then if I look at OPC and start with the 0.77 median value, by the time I come to fly ash, I've dropped down to 0.52, and for blast furnace slag, I drop it down to about 0.28. So there's significant reductions in the greenhouse gas, the carbon tag, the carbon that is associated with the cement. Now, of course, the issues here are, and I'll show this a little later, is the calcium depletion. So I cannot indefinitely keep adding slag or fly ash into the cement, because I'll deplete the calcium in the system. And also a big uncertainty in these two materials, fly ash and slag. They're not manufactured material, they're waste materials. I cannot control the composition of these materials. And therefore, the reactivity of these materials oftentimes dictates how much of this material can I replace in cement. So just a quick look at this cement replacement with fly ash. Now, fly ash itself is something that is produced when we burn coal. Now, India-specific scenario, we are still installing mega thermal power plants that burn coal. So for the next, in the foreseeable future, next 10, 15 years, there is going to be adequate fly ash that's going to be available in India. This is just based on the projections that we have from Coal India, which is producing the coal, and NTPC, which is still continuing to use and continuing to commission new thermal power plants. Now, in the thermal power plant, basically, when I burn coal, what is left behind is the ash, and the ash that I collect from the stack, the flue gas, is this fly ash, and it's a grayish looking material. And the issue is because coal varies significantly from the source, and even from the same source batch to batch, we get a very large variation in the fly ash properties. Now, the fly ash itself could be self-cementing. That is, if it could be hydraulic, I can simply add water to it and start setting and gaining strength. If I have a high percentage of calcium, so that is a class C fly ash. But my bigger problems are it is very variable in composition and it has a low reactivity typically. So when I am going to replace cement with it, I have to expect the overall reactivity of the system to go down. Now, the ground granulated blast furnace slag is again another waste that comes from steel industry. It's basically the gunk that floats on top of the molten steel. That is cooled down very rapidly. It's quenched very quickly, and what we get is something that is very glassy, very reactive, and because of the quenching process. And we find that it has typically a high calcium content. That means it is self-cementing. If I add water to it, it is hydraulic in nature typically. It is reactive, not as reactive as cement, but it's certainly more reactive than fly ash. And the only issue here is it is varying in color, and that makes sometimes the use of blast furnace slag in cement a little tricky because of the different colors associated with the slag. So the challenges that we have currently with the larger use of fly ash and slag in concrete is a large variability in composition. Source to source and within source, batch to batch, is large variation. And typically these are low to medium reactivity materials, and they rely on the secondary effect. So this is not the primary reaction that we're looking at, the secondary reaction. We're utilizing the lime that is produced by cement hydration to produce CSH. So I'll quickly talk about fly ash as cement replacement. And in the India specific scenario, I believe this is one of the key things that we need to look at, because for us, fly ash is something that is available in abundance, at least for the foreseeable future. And the whole point here is that when we look at fly ash, it has lime in a low quantity. Primarily, it has silica and it has alumina. And when I look at cement, that also has lime. Of course, here it has abundance of lime, silica, and alumina. And so when I replace cement with fly ash, essentially what I'm doing is I'm doing a silica replacement. I'm replacing the silica that's coming from cement with the silica that's coming from the fly ash. But in the process, of course, I deplete the lime, because cement is lime rich, whereas this has very low quantity of lime in the fly ash. Now, what about our coal consumption and ash production? If you look at these countries marked in red, these are the countries that are currently producing the largest amount of fly ash, China being number one, we are number two. And like I said, in the foreseeable future, I think at least in the next 10 to 15 years, fly ash is going to be available. So we do have this material that is a waste material, which can be used in cement as a value add and thereby reduce our carbon tag. Now, a little bit of information helps about the use of fly ash. This particularly lately, because the production of fly ash in India is not regulated. Outside of India, if you are to use fly ash, it has to be classified. Whoever produces fly ash or is selling fly ash has to let you know the composition of the fly ash that is being produced. It has to be classified at some level. Physical and the chemical properties should be available and should be made known by the person who's selling. In India, whoever is producing fly ash is under no obligation to disclose the composition of the fly ash. So you basically buy it in the as is, where is condition. You simply just pick it up from the thermal power plant. Now, the way it is produced, the fly ash, is that we have this ash-laden flue gas. It's a very hot gas, about 450 degrees Celsius. As it's exiting from the stack, it is collected through these electrostatic precipitators, and it's collected in different bins, starting from bin 1, 2, all the way to 8. Now, as I increase the bin number, the fineness increases. So basically, more fine the fly ash, more reactive it is. Now, typically previously in India, we were using fly ash in bins 2 and 3 in our construction. But today, after we realized the importance and that we've discovered it's a value-added product, bin 2 and 3 fly ash is slowly being replaced with bin 1, which is coarser fly ash, which is of lower reactivity. So just to show you what fly ash looks like, if you look at fly ash under the microscope, it is basically consists of all these spherical particles, and these spherical particles are basically glass. So these spheres are called cenospheres, and these spheres are primarily glass. The reactive content of fly ash is contained in these glass spheres. So now, when we're talking about fly ash, it is the glassy content of fly ash that is in the cenospheres that we are interested in. And I just want to show you the kind of variability that we typically get in our fly ash. So we collected fly ash from different power plants around the country, and you do a typical oxide analysis. So these are the oxides available present in fly ash, and these are different sources from which we collected fly ash. You find that the primary oxides in fly ash, the silica and the alumina, these are more or less similar within a small range of variation. But if you use these fly ashes in cement, you'd find that the results are night and day. You get a very large variation in compressive strength. So that means clearly that these numbers are not really telling us much if I just look at the oxide composition. The other thing we also notice is that in most Indian fly ashes, the lime content is very, very low. So coming back to the substitution, if you remember, if I'm going to use cement, fly ash in cement, I bring in silica, but that is also questionable because I don't know, something is not really correct about this picture here. But cement is lime rich and this is lime deficient. So basically I'll be reducing the lime content in the system. And we basically developed procedures for determining the reactive silica present in the fly ash. Reactive silica is the silica that is present in that glassy spheres I just showed you. Now, if you look at these fly ashes that we collected, the blue bars here represent the total silica. And you can see the total silica is like a healthy number. It's like 50%, around 5% of the total fly ash is total silica. But if you look at the silica that's present in the glassy spheres, it's a much smaller number than it's less than half of what is indicated by the total silica. And so when we did a little bit more analysis, we find that the difference here is because silica is also present in the form of quartz, and quartz is nothing but sand. So a lot of our fly ash tends to be loaded with sand, and when we are buying fly ash or using fly ash, we're actually paying for this silica, which is the blue bar, but we're only getting this whatever is present in the green bar as the actionable or the material that is of use to us. So this is something that we really need to be concerned about. And also, if you look at the reactive silica content, there's a large variation. And this is what contributes to the very large variation that we see in the strength and even other properties when we start using fly ash. So now this actually tells us that we do have fly ashes which have higher reactive silica in them, like this fly ash B, and we have fly ashes that have very low silica content in them, which is 13%. Now, if I'm going to simply do a 30% swap of cement with fly ash, I will get very different results. And not surprisingly, when we use this particular fly ash, the strengths were double of what we were getting with this fly ash M. So clearly here, then we need to look at these things a little bit more objectively in order to efficiently use the material so that we don't compromise the performance of cement, rather than going with a prescriptive measure of replacing 30% of clinker or 30% of cement with fly ash. Now, of course, in India today, we are making a lot of PPC. Almost, like I said, 70% of our cement consumption is primarily in the form of PPC. Different companies are already making it. But if you look at the Indian code for PPC, the requirements are primarily that of the 30 grade of cement. That is what is currently prescribed. That is what is expected from a PPC. Now, that is partly because the gradation of the cement or the grade of cement is based on the 28-day strength. And because it's a slower reacting material, the higher strength, ultimate strength, is achieved at a much later time. So now coming to this particular thing, what we developed is a rational way of replacing fly ash, cement with fly ash. And we developed what is called an efficiency factor. This comes from thermodynamics. You can actually calculate this. And the whole point is that if I hit an efficiency factor of 1, then I achieve the same performance as what I would get with pure cement or pure clinker-based cement, even on substituting cement with fly ash. Now, if we go by this efficiency factor, I can replace up to 60% of clinker with fly ash and still achieve the same performance. And that is what we've looked at. And just to illustrate this, so we basically looked at a 20% replacement, which is typically what is done with fly ash. So here are here's the cement composition that we have: the alumina, the silica, and the calcium. And you can see the cement has a very high calcium content. 71% of cement is basically calcium oxide. These are the reactive components of fly ash, and you can see that it is completely cement depleted. It's only about 2% is cement, but it has a high reactive silica content. So when I do replace this, I can increase the silica content in my binary blend by bringing in fly ash. Now, we basically, at 20% replacement, we found that it gives us an efficiency factor of 1.34. And we developed a M35 mix, which gave us a compressive strength of 47 megapascal using normal OPC 53 grade cement. But when we did a 20% replacement, because it had an efficiency factor of 1.34, we were starting to get much higher strength of 63 megapascal. But of course, we had to wait much longer because fly ash is lower reacting material. And so I cannot expect this to come up at 28 days. So one of the things that we have to look at, if we are going to look at clinker substitution, is also to relax the requirement of 28-day strength. I just wanted to show you something about this is just test data for different cements. Most of them are, we do have some OPC 43 grade, some PPC grade cements. And what we find is a very large variability. Some of them don't even meet the requirements of the standard, but they are available in the market. So, and a lot of the PPCs in particular show a very large variability. And most of them don't meet this 28-day strength requirement. But by the time you come to 90 days, most of them do meet the strength requirement. So I would like to now quickly talk about fly ash and uses in products and applications. So it is not just that I reduce the clinker factor, so gain in the carbon, but I can use it as a cement substitute to improve the overall performance. And I'm looking at improvements in strength, of course, by optimizing the use of cement in terms of efficiency factor, but I can also improve the durability and the rheology of cement. So I just want to show you a few examples. So controlling heat in mass concreting. Oftentimes I need to have material that is lower reacting. And here fly ash would be very beneficial in reducing the heat and therefore thermal cracking in concrete. Improvements in rheology. When I use fly ash in concrete, I produce a more pumpable concrete. It's because of those glass spheres that are present that act like ball bearings and improve the overall flow of concrete. Roller compacted concrete in pavements, SEC, and in concrete printing applications. Addition of fly ash actually gives some cohesiveness to the mix, helps with the packing, and overall helps in reduction of the water demand of concrete. So some examples of rheology control with fly ash. If I am to make SEC, self-compacting concrete, I need some mechanism to thicken my paste. Otherwise, the aggregate will not hold in suspension. They'll separate out. To get that viscosity control, to increase the stickiness of the paste, oftentimes fly ash is almost essential in producing a mix of SEC. High performance concrete, where I need the other end of the flow control, where I'm talking about slip forming of pavements. Here again, a concrete mix absolutely requires fly ash because it helps with the packing that I need, and it gives it the mix that cohesiveness. Another place where fly ash is an absolute must in controlling the flow is in the use of precast concreting, particularly where you have these hollow core slabs that are being produced. The hollow core slabs are typically produced in an extrusion type mechanism. After the slab is extruded, these holes are supposed to keep their shape. The hole should not collapse on, material should not collapse on itself and close the hole. So that again requires fly ash. The other places where fly ash was been used quite considerably to provide pumping solution is in the construction of course, One World Trade Center, where fly ash was used to get some control in pumping, and also in Burj Khalifa, where concrete is pumped to a height of 601 meters. Now, the other aspect of fly ash is help in durability. If you add fly ash in concrete, you can reduce shrinkage. So that means you have less chance of shrinkage cracking. If I can cut down on shrinkage cracking, then I have a more durable piece of concrete because water cannot enter into concrete, and then my steel is protected for a longer time. And that, of course, is also plays out in terms of RCPT, the penetration. It basically also cuts down on the chloride penetration into concrete. So basically, I'm looking at the use of fly ash from reduction in clinker factor, so that is a plus, and also scoring points on the durability part, which is also required for me to have long-lasting sustainable structures. Coming quickly to slag, which is the other material that is talked about as cement replacement, in slag we have different reactivity, and this, just like fly ash, the reactivity of slag varies considerably. And in ASTM, we don't have this in the BIS standard. Grades are specified. They go from 80, 100 to 120, depending upon the reactivity of the slag. And the way we get the activity index is in terms of the compressive strength of a 50-50 slag Portland blend compared to the compressive strength of ordinary Portland cement blend. And up to 60% replacement of slag, we find that we are able to regain the strength and also produce an improvement in the long-term strength compared to OPC. So slags, therefore, we can replace cements or clinker by almost 70%. And again, the use of slag would help me because it's not as fast reacting as cement, can be used to control the heat production in the structures. If you can see, this is the heat produced by OPC. This is the heat produced when I start adding blast furnace slag in it, and that would play a role in controlling thermal cracking. And this is where slag perhaps is most beneficial, is in achievement of diffusion control, because slag, excuse me, added to concrete has a tremendous chloride binding capacity. And if you look at, these are the tests of chloride penetration obtained from the chloride bonding test. This is the chloride profile in control, which is normal concrete. And by the time I add blast furnace slag, you see the profile is limited only to the surface layer. And of course, also fly ash cuts this down. So these supplementary cementitious materials are helping on several fronts. One is improving the durability in the form of shrinkage, heat, and also chloride penetration. So here is a quick summary of different performance indicators. I have ordinary Portland cement. It has a high heat of hydration, high permeability. Of course, I can densify the matrix, but typically, if you look at performance characteristics like shrinkage, OPC has a high shrinkage. It has a lower alkali aggregate reaction resistance, less resistance to sulfate attack, depending upon the sulfate content or the aluminate content. And the resistance to chloride induced corrosion is, if I take that as a benchmark, then with PPC and PSC, I basically score higher on all of these performance indicators. The only thing that perhaps one needs to look at carefully is the carbonation induced corrosion, where it has been reported that PPC and PSC perhaps have lower carbonation induced or the higher risk to carbonation induced corrosion. Now, what about using blends of slag and fly ash? So where I can beneficiate from both. Slag gives me a slightly higher reactivity. It gives me a slightly better chloride binding capacity, and it gives me better strength performance. And fly ash helps me with the rheology and long-term strength. So I can basically start combining these, and this is already in play. So we have ternary blends that have successfully been used. So you see that the Reliance Stadium in Houston, Texas, it was a ternary blend of slag and Class C fly ash, and they were targeting 124 megapascal strength. In Canada, slag and silica fume. So they're bringing in an additional material, and this has been conventionally used for 80 megapascal concrete. Japan has been using slag cements for about 70 megapascal concrete strengths routinely. So now, if I'm talking about high performance concrete in service, so one of the biggest hitches that we have is traditionally we use 28-day strength as our benchmark. Now, this becomes a problem if I'm going to start using lower reactive supplementary cementitious materials when I'm using them as clinker substitutes. And the other thing is, when we have structures like a high-rise building, achieving fast strength is really not required, because if I look at a typical construction, even with a 7-day slab cycle, if I have a high-rise building, the columns on the lower floor will not see loading until much later than a few months. And so the requirement for this 28-day strength is misplaced. And perhaps a 90-day compressive strength may be a better indicator of strength as it is applicable for use with supplementary cementitious material. And I think this is one of those things that we have to look at more carefully if we are going to promote the use of more of blended cements. Now, so we've looked at the ternary and binary blends, where we are looking at clinker substitution with fly ash. There are other cements that are also being produced. One of them is the LC3 cement, where we bring in calcined clay and limestone as a substitute for clinker. And with this, we are able to achieve about 50% clinker substitution with calcined clay. And the calcined clay itself doesn't have to be very high grade clay. And so potentially there are savings here with this material. Now, the other way of looking at materials is to look at alternate cement chemistry, which does not start with limestone. And here we have this whole group of cements binders that we call alkali activated binders, where you start with a waste material, which is a source of silica or alumina, such as fly ash, activated using alkalis, and then we are able to produce cements. And one class of cements is called geopolymers. The other cements are typically called alkali activated slag based cements. And the whole point here is to get a source of silica or alumina. Currently, the cheaply available sources of silica and alumina are fly ash and slag. And we basically activate it using alkalis. One can optimize the activator ratio, and we can start now making these cements, which are derived completely from waste, and we are getting away from limestone. So basically, the carbon tag of this material is very, very small. So this is also a concurrent parallel development that is taking place, which perhaps may see a larger role in the future. Now, coming to so far we've looked at the material aspects. Now, I quickly want to conclude by talking about the last picture, last piece in the puzzle, which is the efficiency in design and construction. So we've looked at the material aspects. We've also looked at carbon sequestration. So coming now to the fact that suppose I'm still using limestone-based cements, clinkers, then we have to look at 22% reductions in the total carbon by efficient design and construction. So here we're talking about design optimization. That is, we bring in concepts of optimization and we basically use material efficiently, produce structures with lower use of material that give me the same level of structural performance. Then, of course, construction site efficiencies. We really have to improve this. That means adopting technology on the construction site. So efficient construction is something that is essential, and we have to look at the current forms of construction, because we are currently limited to a large extent by forming on site. That means, of course, bringing in more of precasting materials that are formed off site in an efficient manner. And one of the current limitations that we have is with the use of rectilinear forms, and that is, I currently make all my beams to be rectangular because they're easy to make. Now, a rectangular beam is not the most efficient structure. Now, which means that we really need to look at our structural forms carefully, optimize the use of material, which perhaps, if it comes to practical application, is not possible with the conventional method of construction. So we need to start looking at alternate methods of construction, such as form-free construction. And this is where techniques like methods like 3D concrete printing are coming into the fore. So if you look at 3D concrete printing, it has caught everybody's fancy. And that is, we're looking at something like this, where you have a robot that's perhaps going around constructing a structure. And of course, it's all digital construction and all things fancy. But perhaps what people are missing in this whole, the glitzy appeal of 3D concrete printing is this avenue that it offers us for lean construction. And this is perhaps what a lot of us are more excited about than the other things. And that is, I can start printing structures following the simple principle of material follows force. I can deposit material where it is required, not be forced by the limitation of the formwork. I don't have to produce rectangular beams. I can look at the force flow inside the structure and deposit material when and where it is required. And I can produce form optimized structures that are light and give you the same structural performance with much lesser use of material. So they're lighter structures which are very efficient. So therefore, I cut down on the requirement of concrete. So just to give you an example, suppose I take a beam and I apply a load on this. We know that typically we'll have a compressive strut that forms here, and then we provide a tension tie. Of course, a very simple example here. Now, what I can do here is start playing with this form and look to deposit concrete along here in this arch-like, in an arch-like fashion, and then provide a tension tie. And using this concept, actually, we developed a topology optimized bridge where the shape has been optimized to provide the force flow such that this beam can now be represented using this arch type shape with this with these tie elements. And I can print this. In fact, we have printed this bridge at IIT Hyderabad. And this gives me an almost similar performance as the solid beam of concrete. And this, in terms of weight, is about roughly about 1/5 or 1/6 of the weight of the solid beam. So I have achieved tremendous material savings without compromising the capacity or the performance. Now, of course, there are a few challenges with 3D printing. One of the biggest challenges, of course, is incorporation of reinforcement into 3D concrete printing. But work is happening very rapidly, quick, a lot of research is happening, and even that will become reality very soon. So with that, in fact, I'd like to conclude my presentation. I know I've covered a large scape of things, starting from materials to structures. But the whole idea is that we all have to move towards net zero. It's a mandate now. We have to look at achieving net zero. There are several opportunities, and of course, there are multiple challenges in this. The only way we'll hit net zero is by looking at concrete as a material and look at the carbon that goes into the production of the material, tackle the material related issue, and also look at the use of this concrete in structures, to use efficient structures with less usage of materials. So this is the message I was trying to drive. And with this, I'd like to conclude and open the floor for any questions or comments.
Good evening. Thanks for the presentation. Now, Latashri from QCrete will ask questions on behalf of audience. Yes.
Good evening, sir. We have received lots of questions. I will take few of them. First question: is it possible to ensure net zero target with locally available material? It is asked by Pawan Kumar V.
Sorry, can you repeat that question? It's difficult to, the audio is not very clear.
Does it possible to ensure net zero target with locally available materials?
Well, that is the other challenge. In fact, this is a good question because it has to be local. So if we are starting to look at materials with a long lead, then that again adds to the transportation and the carbon that goes with the transportation. So we have to look for local solutions.
Okay. Thank you, sir. Next question: how to quantify the durability of concrete in terms of performance-based parameters at the time of concrete mix design? It is asked
Yes.
Dr. Kameshwara Rao.
No, this I think is another very interesting question, and that is, how do I relate performance with some durability measure? So now, durability measures are nothing but
Hello.
developing accelerated tests. So if I can do accelerated testing, just like I would do for compressive strength, then I have a way of testing this material in a rapid manner. Then the other thing is to translate the information that I have from the test into predicting the service life of the structure. So to give you an example, suppose I was to look at chloride diffusion into concrete. Now I can do tests and get measures of chloride diffusion into concrete. Now I need to translate this information that I have about my mix by considering the environment that it is going to be placed in, and then be able to predict how long will the steel inside this concrete remain in a passive state. Now, if I don't, if I am able to, if I have models that I am able to predict this, or if I have some method, some expressions, some equations that are available, then I've completely closed the loop. Now, the concrete mix that I start with, if it does not give me the required performance, if it does not last long enough, then I have to go back and revise my mix and make sure that I satisfy the performance requirement. Now, the performance requirement will be satisfied in terms of the durability measures. So this is what will have to be done in performance-based design, where you'll have to run durability-based tests, then use the measures that you get from the durability test to predict the life of the structure, and be prepared to change your mix design based on the performance in the durability test.
Thank you, sir. Next question. Your thoughts on using cement kiln dust as an activator in geopolymer concrete. It is asked by Subramanian Shivaramakrishnan.
Okay. Yeah, I mean, we'll have to look at the composition of the cement kiln dust. The issue is that cement kiln dust would be rich in calcium. So it will not be a good source for producing geopolymers. What we have seen is that if you take a calcium-rich material, typically, if you activate it, what you get is a reaction product that looks very similar to CSH, or calcium silicate hydrate, what we get from cement hydration. It's slightly different because this material will have alumina substitution in the CSH structure. But that then is not like a geopolymer. Geopolymer typically requires low calcium silica source. So cement kiln dust can be used. You can alkali activate it, but you may not get a geopolymer at the end of it.
Okay. Thank you, sir. Next question. Use of bottom ash as aggregate replacement is also another way to make a concrete greener.
Yes,
It is asked by Ramachandra V.
absolutely. Yeah, absolutely. Bottom ash and basically aggregate is the one of those the silent entities in concrete that we have not paid adequate attention to. And now our revised IS code allows the use of several alternate aggregates, including manufactured aggregates. And the reason for that is because our natural stock of aggregate stone is depleting. So, and in fact, good stone is not available in several parts of the country. So we have no choice but to substitute the aggregate. And so we are bringing in things like recycled concrete aggregate. Copper slag is also allowed as for use as aggregate, and the bottom ash is also a good source that can be used as aggregate. But of course, with all of these, one has to be aware of the reduction in the performance of the concrete, and we would have to look at measures of compensating for the reduction in the performance.
Thank you, sir. Next question. Your thoughts on UHPC in lean construction. It is asked by Subramanian Shivaramakrishnan.
Yeah. UHPC is this new form of concrete, which is now being, I would say, looked at very seriously, particularly in the bridge sector. So, and the advantage you gain with this material is that because it is stronger, more ductile than concrete, I'm able to make longer span bridges with lesser use of material. And so there's a tremendous saving in the material usage with this material. So yes, I mean, there is a case for the use of UHPC in structures, making lightweight structures, efficient structures. And I think from what I see, perhaps bridges are natural, where it's a natural, where it finds natural applications. There may be other applications as well where one can certainly look at this material to provide the performance with very small use or limited use of this in terms of quantity.
Okay, thank you, sir. Next question. Is self-compacting concrete a solution to achieving net zero? It is asked by Ayo.
Self-compacting concrete by itself would not be a solution to achieving net zero. Self-compacting concrete is concrete that I would use for a specific performance, that is self-leveling performance. Now, I'm achieving certain pluses from there. That is, it is being used a lot for form finish concrete, where I don't need to plaster. Therefore, I save on material. I get beautiful finishes which comes out of the form work. Less use of labor, and so there are savings on the other front. but by itself it has a much higher binder content. So unless I can offset that binder content, the increased binder content with the use of more fines and other material, we cannot by itself call it as very sustainable or something that will take me to net zero by itself.
Hello. Good evening.
Yes.
Because a lot of other questions are there, but due to lack of time, we cannot get answer for all the questions. They can write to us and we will send it to Dr. Subramaniam Garu and then we'll get back. On behalf of QCrete Readymix India Private Limited, we thank audience for attending and making use of the wisdom and experience of Dr. Subramaniam sir. We once again thank on behalf of QCrete Dr. Subramaniam sir for delivering this wonderful knowledge sharing session. Really many of the information, lot of information. I have been personally working on concrete and GGBS for quite some time now, but some of the information provided today is eye-opener to me and possibly can be used by many of the concrete technologies whoever have attended this wonderful session from Dr. Subramaniam. A lot of information on sustainability was also given by Dr. Subramaniam Garu. We thank once again Subramaniam sir for accepting and coming on this platform, and is an honor for us. We also thank Dr. Sunita Nair and all from Kochi ICI for being with us on this webinar. On behalf of QCrete, once again, we thank QCrete staff, Neelamma and Latashri for being with us today for helping to conduct this webinar in a good way. We once again thank the audience. We'll see you next time. Thanks once again, Dr. Subramaniam sir. Nice of you.
Thank you. Thank you.
Thank you.